Hi, so we are Group 6 and we'll be talking about the model MT5, which is a massively multilingual pre-trained text-to-text transformer model. Let's quickly start with an introduction. On July 2020, Google released this model called T5, and this is a text-to-text transformer model which achieved state-of-the-art results on a wide variety of English language NLP tasks, such as question answering, summarization, and so on. This model was able to perform better than some of the well-known models such as BERT and BART. However, since this was trained only on one language, which is English, it kind of limits the usage to 80% of the world population who does not speak English. With this motivation, the authors worked on creating a multilingual version of the T5 model, which is called MT5. And this model is very similar to the models you would have heard of, which are MBERT and MBART. So now that we have a quick introduction and we know that it is based on T5 model, we'll start with a background on T5 model and the data set used for the T5 model, which is basically C4. Now, let's talk about the distinguishing features for T5. One of the key features is the text-to-text framework. So the text-to-text framework is basically a unified framework in which we give the model a text input and it outputs text. So as you know this kind of framework which will work very well for generation or machine translation tasks. But let's say if we take classification or if we are expecting an integer output, this is going to fail. And in order to fix this, the authors they created a prefix and they're adding this prefix in the input. For example, let's say if you talk about this, the first example here, which is translate English to German, that is good. So the prefix here, translate English to German, is basically giving the instruction to the machine that, that is good has to be translated from English to German. Similarly, if you look at the third example here, like you have the sentence one and sentence two, but the prefix STSB is basically giving the instruction that it is trying to, it has to find the similarity between these two sentences. And with this unified framework, we are able to just train one single model for all the diverse NLP tasks that we have. Now, moving on to the T5 architecture and training. So here the authors have used the fill in the blank or the span corruption objective. What this does is, like, let's say if you take the original text, thank you for inviting me to your party last week, then the for inviting phrase is basically marked as a sentinel token X here, and the word last is marked as the Y. And the model is expected to output the phrase for inviting and last. So this type of objective is basically called span correction. And in this paper, the authors have used the mean span length of 3, and almost like 50% of the text was corrupted for the training of the pre-training of the model. Now, the other distinguishing feature is here the authors have used a mixture of unsupervised and supervised tasks. So what you're seeing above is basically an example of unsupervised tasks. But what we discussed in the earlier slide was a supervised example. So they just use a mixture of both of these kind of NLP tasks to pre-train the T5 model. And the architecture which they have used is basically an encoder-decoder architecture. And as we all know that, if we have similar layers in encoder and decoder, this model will have twice the number of parameters as compared to encoder only or decoder only. And this will increase the computational cost of this particular model. So in order to address this problem, they have shared the parameters between encoder and decoder, and they showed that there is no degradation in the performance of this encoder-decoder training. Moving on to the data set which was used, and which is one of the very key important features of T5, which is the scale. For this, they used the common crawl web scrape dataset, and this dataset was approximately of the size of 20 terabytes for the month of April, for which they used different filtering techniques in order to get the right corpus for the training of the model, such as they use LangDetect 2 to identify the English language text only, and they use some deduplication techniques to filter out the repeated text in the corpus, post which they got a filtered 750 GB English language text, which had almost 1 trillion tokens, and they trained different sizes of the model for the further fine-tuning usage. And some of the popular ones are like the small 60 million parameters based to 220 million parameters. And this sort of concludes our background on the T5 model and the C4 dataset. So here now we'll move on to the multilingual version of this. I'll quickly talk about how the multilingual version of the C4 dataset, which we just talked about, is created for the MT5 model. So moving on to the next slide. So for MC4, we basically scrape the dataset for 71 months instead of 1 month. And this, if you can imagine the size of the dataset, 71 into 20 TB, this was huge. And the authors basically filtered this size dataset for 100 languages using tools like CLD3, which identifies what language the text is in. And they used filtering techniques which are very similar to C4 to create a corpus which had 101 languages. And then basically this was a massive data set which was created to train the model MT5. With this, I'll pass over to Tazeen to talk more about the MT5 architecture and the model training.
Now, talking about the MT5 model, the model architecture and training procedure that we use for MT5 closely follows that of the T5. Specifically, it's based on the T5 1.1 recipe. One of the differences between the T5 and the MT5 is, however, the use of gated exponential linear units. The GEGLU activation function was found to be effective in reducing the number of parameters and computation required in large-scale language modeling and translational tasks, making it suitable for use in the MT5 model. It has been shown to perform better than the standard GLU function used in the T5 model, which can suffer from vanishing gradients and overfitting when applied to large models. Another important aspect in MT5 is the sampling techniques used for high resource and low resource languages. It is performed during training to balance the amount of data seen for each language. Specifically, the sampling probability is inversely proportional to the square root of the number of available examples for a language. For high resource languages with many examples, the sampling strategy results in a reduction of the number of examples used during training, which can help prevent overfitting and improve model generalization. For low resource languages with fewer examples, the sampling strategy results in an increase in the number of examples used during training, which can improve performance on these languages by providing more training data. Another important aspect of MT5 is increasing the vocabulary size to 250,000 word pieces. The fact that MT5 model covers over 100 languages necessitates a larger vocabulary. Subword units are fragments of words that are used to represent the full word in the model's vocabulary. By breaking words into subwords unit, the model can better handle out of vocabulary words and rare words that may not be present in the training data. In the case of MT5, the researchers increased the vocabulary size from the 32,000 subword units used in the original T5 model to 100,000 subword units. However, one drawback of this is that the larger vocabulary size also requires more memory and computational resources to train and use the model. Now, moving on to the next part of the presentation, which will be related models, experiments, and size of the MT5 model. So, starting with the comparison to related models, the first model being compared to MT5 was the MBERT, which is a multilingual version of BERT trained up to 104 languages. It is very similar to the approach taken with MT5 in that MBERT follows BERT recipe as close as possible. The primary difference is the training set. Instead of training on English Wikipedia and Toronto Book Corpus, MBERT is trained on up to 104 languages from Wikipedia. Second is XLM, a cross-lingual language model that uses a combination of language-specific and shared encoders. It is also based on BERT but applies improved methods for pre-training multilingual language models, including explicitly cross-lingual pre-training objectives. Many pre-trained versions of XLM have been released. The most massively multilingual variant was trained on 100 languages from Wikipedia. Another XLM variant is the XLM-R, which is an improved version of XLM based on the Roberta model. It is also trained with a cross-lingual masked language modeling objective on data in 100 languages from Common Crawl. To improve the pre-training data quality here, pages from Common Crawl were filtered by an n-gram language model trained on Wikipedia. MBART, which is another multilingual pre-trained model, is developed by Facebook AI Research. It is trained with a combination of span, masking, and sentence shuffling objectives on a subset of 25 languages from the same data as XLMR. Last but not the least, the MARGE model is a pre-trained sequence-to-sequence model learned with an unsupervised multilingual multi-document paraphrasing objective. It is trained to reconstruct a document in one language by retrieving documents in other languages. It uses data in 26 languages from Wikipedia and CC News. Now, moving on to the experiments conducted in this research paper, there are 6 tasks conducted, all coming from the extreme multilingual benchmark. Starting with sentence pairing, the cross-lingual natural language inference, or the XNLI experiment, is a benchmark task for evaluating the performance of natural language inference models across multiple languages. In this task, the goal is to predict the relationship between two sentences, which can be one of the 3 classes: entailment, contradiction, or neutral. The XNLI dataset is composed of examples in 15 languages and is based on the multi-genre natural language inference corpus in English. The second part of the sentence pairing is PAUSE-X, or parallel cross-lingual wikis. It is another benchmark task for evaluating the performance of natural language understanding models across multiple languages. The PAUSE-X data contains sentence pairs in 6 languages, and the pairs are labeled as paraphrase or not paraphrase. It evaluates the ability of models to perform cross-lingual sentence matching, where the model is trained on one language and evaluated on another language. The second type of testing was the named entity recognition, which was done on the Wiki and NER dataset. The Wiki and corpus is a multilingual and large-scale corpus that can be used to evaluate and named entities such as person, organization, and location. However, the dataset here is restricted to 40 languages from the extreme benchmark in this research paper. Last part of the extreme multilingual benchmark were the question answering experiments. It included XQuad, TidyQA, and MLQA. XQuad is a benchmark dataset for evaluating cross-lingual question answering performance. It consists of a subset of 240 paragraphs and 1190 question answer pairs with their professional translations into 10 languages. Consequently, the dataset is entirely parallel across 11 languages. MLQA is an extractive QA evaluation benchmark intended to spur research in this area. It consists of over 12,000 question answering instances in English and 5,000 in 7 other languages. Last is the TidyQA, a question answering dataset covering 11 typological diverse languages with 200,000 question answers pairs. Moving on to the different sizes of mT5 model. There are 5 sizes which are very similar to the original T5 recipe. The smallest being the mT5 small with only 300 million parameters, and the largest being mT5 XXL having 13 billion parameters. The increase in the parameter counts compared to the corresponding T5 model variant come from the larger vocabulary used in mT5. Now moving on, Sudiksha will be comparing XLMR and mT5 configurations and further on.
So before we jump into the XLMR and mT5 configuration, we'll compare them. XLMR is an encoder-only model, while mT5 is an encoder-decoder model. Hence, it has almost double the parameters. Although the cost of processing in XLMR is not too different from mT5, which produces T+2 tokens, since the decoder for classification produces the class label and an N of sequence token. XLMR pre-trains for more steps compared to the mT5 model, which pre-trains for 1 million steps. XLMR has over 6 times more tokens in pre-training compared to mT5, which has almost 1 trillion input tokens. XLMR has smaller pre-training corpus CC100, which is 20 times smaller than mT5's MC4 corpus. Moving on to the mT5 model configuration, mT5 uses the same inverse square root learning rate as T5 during pre-training. The dropout is not applied during pre-training. The same self-supervised objective as T5 is used for pre-training in mT5, with 15% of tokens masked and an average noise span length of 3. For fine-tuning, a constant learning rate of 0.001 and a dropout rate of 0.1 is used. A batch size of 2 to the power 17 is used for most of the tasks, with exception for Wiki AN and NER 0-shot, where we use 2 to the power 16, while XNLI we use 2 to the power 20. The checkpoints are saved every 200 steps for early stopping. Moving on to the fine-tuning, which is the technique of using a pre-trained language model and adapting it to a specific downstream task. The MT5 model was fine-tuned using 3 different techniques. The first, zero-shot fine-tuning. In this technique, the model is fine-tuned only on English data, and then it is evaluated on tasks in multiple languages without any additional training. This approach tests the model's generalizability to new languages without any explicit training. Second, the translate-train fine-tuning. In this technique, the model is fine-tuned on English data, and then additional data is added through machine translations into each of the target languages. This approach tests the model's ability to learn from machine translations and to adapt to new languages. Third, in-language multitask fine-tuning. In this technique, the model is fine-tuned on gold data in all target languages. This approach tests the model's ability to learn from data in multiple languages and to perform well on multiple tasks simultaneously. Now, moving over to the results of our experiments, we compare it with the existing state-of-the-art models, and what we observe is the MT5 double XL, our largest model, is exceeding the state-of-the-art on all the classification and question-answer tasks. Hence, we can say that scaling up a simple pre-training recipe could be a viable alternative to more complex techniques. Similarly, during the fine-tuning variations, the translate-train setting, where we model is fine-tuned on a combination of labeled English data and machine translations, we exceed the state-of-the-art on all extreme classification and question-answer tasks. Hence, we can say that MT5 model is highly effective for cross-lingual transfer learning, and its performance can be further improved by fine-tuning on data in multiple languages or through machine translations. Moving over, in this graph, we compare the human versus the 3 fine-tuning experiments basis their F1 scores. We observe the performance improves with increased model capacity, which is crucial in improving it in the absence of gold multilingual data. Training on gold data sets in-language multitask achieves better performance than using weakly supervised data in translate-train or English-only zero-shot data for the smaller models. The importance of in-language training data, it decreases with the model scale, which shows that machine translation of monolingual data, it brings diminishing returns as the model capacity increases. So we can avoid the expensive task of annotating data in more than one language if we use larger models. We have seen that massively multilingual models may underperform, next slide please, may underperform on a specific language compared to a dedicated model, and hence we compare the T5 and MT5, and we observe that the small and base MT5 models, they perform worse than the English-only T5 model, but the larger models close the gap. Hence, we can say there could be a turning point where model capacity is sufficient to effectively learn multiple languages without significant inference effects. Moving over to ablations, we tried 6 different ablations using the large model as the baseline to see whether our chosen settings are right or not. First, we increase the dropout to 0.1 to avoid overfitting. Second, we decrease the sequence length to 512, same as T5. Third, we increase the average noise span length in pre-training to 10. Fourth, we adjust the language sampling exponent alpha to 0.7 and 0.2. Fifth, we turn off the line length filter in MC4. Sixth, we supplement MC4 with Wikipedia data. And we observe the average XNLI score is lower than our baseline model in all of these cases, justifying that we have chosen the correct parameters. Now I transfer to Vamsi for zero-shot generation.
In zero-shot generalization, the generative models like MT5 can predict arbitrary predictions. So there should be a control on what it can predict. MT5 is having a trouble in this case in zero-shot generalization. So what the trouble it is having is that it is having trouble to form a well-formed prediction in languages other than the language it was fine-tuned on. This might be due to the less number of constraints that are present due to the prediction. And quad zero-shot task, most of the errors that it has performed is due to accidental translation to English, which we'll see in the further slides. Coming to the illegal predictions, in span selection tasks such as quad, where you have to select particular span of words in the question as an answer. In this span length task, models like T5, generative models like T5 perform really well. But in the case of cross-lingual zero-shot span selection task, MT5 is not able to perform that well because it was fine-tuned on English, but it is being tested on other language. So this illegal predictions can be categorized into three categories. The first one is normalization, the second one is grammatical adjustment, and the third one is accidental translation. So I'll be talking about normalization now. So normalization is a case where the target and the prediction just vary by a single equivalent Unicode. I mean, that means that the Unicode that is to be predicted and the Unicode that is predicted are nearly equivalent. And you can see in the case here in the right hand side top corner, you can see that percentage is replaced by full width is replaced by percentage, and normal subscript normal script A superscript A is replaced by normal script A. So in this case, in the normalization errors, this can be converted to true targets by just changing a single character. And coming to the grammatical adjustments, so grammatical adjustments are cases where there is a minor morphological changes that occur to the target text. This occur because the target texts are generally not well-formed answers. So you can see in the case here, so in the right hand side in the middle part, so in the Russian slang, I don't know Russian, so I'm not able to explain it, but the main concept here is that the words here cannot stand on themselves. So the model is predicting a morphological change sentence. So this is grammatical adjustment. Then moving to the accidental translation. So accidental translations are where the model the model is failing to translate the answer into the target language. So you can see in the case here in the bottom part of this picture. So the target answer was in Spanish, but it translated the same in English and it has given as a prediction. And there is one even strange thing that can be observed here. In the last example, the model had to predict chloroplast in Russian because it's a target language, but you can see that it has predicted the first four characters correctly in the English, wrongly in the English, then it has started predicting them in the correct language, that is Russian. So the model is having a trouble initially to predict it in the target language. So the possible solution that the paper has given is that we can perform task-specific fine-tuning, which can decrease the probabilities of these errors. But there are some drawbacks because of using this method. The first drawback is that it is against our goal of general text-to-text interface. So we want to use as much less fine-tuning as we want. But if you are fine-tuning to every task, then it is against our goal. And the second drawback is that if you are fine-tuning to every task, it becomes very hard to fine-tune it to the open-ended zero-shot generative task like summarization, where fine-tuning would be very difficult in this case. So this is not a possible solution. And the other possible solution that had been provided by the paper is related to forgetting. So we are pre-training on all the languages, but we are fine-tuning it only on the English. So model is generally forgetting the original languages that it has been trained on. So we have to make a way that the model does not forget the original languages. So to do this, during the fine-tuning step, we add a bit of unsupervised multilingual pre-training data along with the English fine-tuning data. So what that does is it will make the model remember the target languages too. So doing that has increased the accuracy to 70% for small and base models. And the process it has been done is that we have decreased the number of tokens that are present in the multilingual pre-training, and we have changed the alpha value from 0.3 to 0.1 so that we can get an equal representation of all the languages. So doing this, we got an increase in the accuracy. The conclusion part of the paper contained that they have introduced mT5, mC4, which are multilingual variants of T5 and C4, and they have demonstrated that T5 recipe can be applied directly to multilingual. And the last point which they have shown is that zero-shot evaluations and their solution for that issue. Thank you. Do email us. We are including our email in the link below.